Chain of events, cause and effect. We analyse what went right and what went wrong as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. Causality is part of the Engineered Network. For other great shows, visit engineered.network today. Piper Alpha. I've heard those words my entire engineering career. And it's held up as the poster child of how not to do business. Not just in oil and gas, but for maintenance activities in whatever industry you may be in engineering. Ultimately, it was a disaster that was driven through lack of coordination and perhaps miscommunication. In 1 hour and 30 minutes, the 12 years of otherwise successful operation of the Piper Alpha oil and gas platform ended in a fiery inferno in the middle of the North Sea. The platform had operated safely, producing crude oil, natural gas, LPG. It was a huge platform, weighing in at 20,000 tonnes. The Piper oil field off the coast of Scotland had several neighbouring platforms. Tartan and Claymore were all interconnected with Piper to pump oil and gas back to shore for processing via undersea pipelines. The platforms themselves were visible to each other on a clear day. The oil platforms offshore were scattered around a large area, and many were interconnected and had common pipework corridors along the ocean floor to bring that oil back to the mainland to be processed. So standing on the deck on one platform, you could usually see many others, depending upon where you were. Depending upon the composition of that oil that you're extracting from beneath the seabed, you can end up with crude oil itself, of course, as well as different blends of natural gases. The quantities and compositions would vary from well to well and oil field to oil field. The natural gases are composed of methane primarily, as well as heavier hydrocarbons like ethane, pentane, butane, and so on, as well as some undesirable byproducts like hydrogen sulfide, for example. The heavier elements drop out of the gas when it's cooled down, and those that condense out are referred to as condensate. Condensate produced from oil wells is also typically referred to as lease condensate. So specifically, what happened at Piper Alpha? On Wednesday, July the 6th, 1988, off the coast of Scotland, in the middle of the North Sea, 167 kilometres out from the coast of Aberdeen, 226 men worked aboard the Piper Alpha oil platform. It was a normal enough day. At 7:45 in the morning, a permit was issued for the routine testing of a safety valve. Now, this testing required the removal of the valve from its usual position in the pipework. It was tested independently and then returned to its position in the pipework. Permit number 23434 for PSV 504, time 7:40 a.m., with the note, open pipework to be fitted with flanges, and noted that the condensate pump associated with that valve should not be turned on and should remain isolated. That area of the plant also had other preventative maintenance activities happening in parallel. And another permit that was intended to run at the same time as the safety valves permit was just for the general overhaul of that pump that was associated with that PSV. That permit was considered lower priority. It had been opened, but no works had begun on that permit that day. At 12 o'clock, lunchtime, on the production deck, the safety valve has now been removed, and they are on track to finish their works by 6 p.m., the end of their shift. Just a normal maintenance procedure. But by 6 p.m., at the end of the day shift, the work on the safety valve wasn't finished quite in time. The pump that was connected to it was shut down, signed out of service, and in place of the safety valve, as per the permit that was issued that morning for the safety valve, a blind was fixed to the pipework opening, which is just a flat piece of steel designed to stop any gases from escaping from that pipe should it be pressurized. At night shift, the shift change over on the on-duty operator, unfortunately, was busy at the time with another conversation, and rather than interrupt the engineer who had the safety valve permit, who'd been involved during the safety valve works that day, decided to place it in the appropriate permit box and left without speaking to the new shift operator. 62 men running the rig on night shift. Again, just a normal enough night shift. At 9:45 p.m., however, things started to unravel. There was an urgent alarm, it was an audible alarm, on the condensate pump. It had tripped. So these particular condensate pumps pressurized to LPG at a pressure of about 78 atmospheres. And these pumps would trip from time to time. You know, they were used to getting this alarm. It would happen like hundreds of times, you know, in any given year. It was normal enough to get it. It was routine enough. Usual procedure, restart the pump, away you go. And they tried that multiple times to restart the pump, but they just couldn't get it to restart. The problem is that once the pressure drops, because they were using that compressed condensate to run the main generators that powered the entire platform, essentially they had about 30 minutes left before the tanks essentially would cause the safety system to shut down the rig. It was not a safety issue, but it was a production issue because the rig generated its own mains power from the condensate, and although they had backup generators, diesel generators, they wouldn't let the rig continue to produce. You'd still have lights and basic power, but you wouldn't have enough to actually produce oil. So, the backup pump, ordinarily, you would simply go to the backup pump because there's two of these in parallel. Don't have one, that's what the backup's for. But that, unfortunately, was the one that was offline for maintenance. The operator who was on shift at the time checked the permit and determined that the maintenance work on the pump itself hadn't begun yet. And it hadn't, not on the pump, and decided to sign it back into service, not realizing that the PSV had been removed, because that was on a different permit. 9:55 p.m., a minor gas leak was detected on the deck above where the pumps were located. The operator silences the alarm the first time and then warns the operators on the deck that something might be wrong. Very shortly after, multiple alarms followed, and finally, a high-level gas alarm sounded. All of these alarms came from Module C. At exactly 10 p.m., the first explosion occurred, and it shook the entire platform, shortly followed by a second. The rig was now on fire. The operator hit the plant shutdown, and that killed everything. All the electrical power, all the valves closed. It shut down the rig. Unfortunately, the explosion had destroyed the main alarm panel. There was no power. The platform went completely silent. No alarms, nothing, just the sound of the fire burning. Now, on these oil platforms at the time, they were doing a lot of work on the pipes underneath the ocean. So there were several boats in the area at the time laying undersea pipes. And they witnessed this whole series of events unfolding. Many of it was caught on camera as it happened. And those photographs became very important later when trying to understand what went wrong. And at 10:20 p.m., an enormous explosion occurred. Now, the canteen is where workers were supposed to assemble in the case of an emergency. That was part of their training and the evacuation plan, because the canteen is directly adjacent to the helipad. Now, the workers that had gone to the canteen as per their training, they didn't know that the helipad was already in flames, and there was certainly no help coming to the canteen. At 10:50 p.m., another huge explosion took out a rescue boat with several initial survivors that were stranded underneath the platform. People were jumping from various heights into the water. What most people don't realize is that these oil platforms have to be above the maximum swell heights that you get in that part of the world, in that ocean. And in order to do that, these platforms are very, very high off above the water. And on that time, on that night, most people from the deck, you could not jump from the deck and survive landing in that water. People that were trying to escape would climb down as far as they could. Some dove into the water from as little as 6 meters, some from 20, and one person even survived jumping from a height of 45 meters above the sea to escape the flames. At 11:20 p.m., yet another huge explosion takes out the crane, the drilling deck. The entire platform now begins to tip towards the north. By 12:15 a.m., the entire platform had been destroyed. 167 people, including 2 rescue workers, died. The investigation was led by Lord Cullen. It was a royal commission, and he brought to bear 87 professionals in the field to determine exactly what went wrong. But the biggest problem in understanding Piper Alpha was so much of the evidence had been destroyed by the blaze, and reconstructing the evidence was extremely difficult. The investigation was 2 years long. There were countless interviews with survivors, photos and videos from surrounding boats, nearby platforms, with the primary form of evidence, since recovering evidence from the melted wreck at the bottom of the sea was very time-consuming and difficult. What they did know was that the initial explosion did come from Module C, and based on the color of the explosion's flame, they knew it had to be caused by condensate. They also knew from testimonies from people that survived that works were being carried out on the safety valve. Because they didn't have anything left of the safety valve or the flange it was attached to, they did some equivalence testing. And by that, I mean they took the same pump, the same pipe, and the same valve and blinds, and they did some tests to try and replicate the results. What they found was that the blind could not have possibly been tightened using the correct tools. So by testing on an identical system with varying amounts of tightening torque pressures, the investigators concluded the blind could only have been hand tightened if it was going to leak any condensate. Even the slightest amount of tensioning of the bolts evenly with a spanner of any kind would have prevented any gas leaking. When they were priming the standby condensate pump trying to get it started, the loosely tightened blind let enough gas escape to trigger the first of the gas detector alarms. That was what they heard in the control room initially. The condensate pumps were located on a different floor to the safety valve, so the operator could not visibly tell that his actions in priming and starting that standby condensate pump that was supposed to be tagged out was actually causing that gas leak, because it was on a completely different floor. You couldn't see it. Now, there are firewalls that are fitted between the modules. They're designed to slow down or completely stop fires from spreading in the event that there is a fire in a single module. Photographs taken from a nearby ship at the time show that the second explosion came from Module B. The problem seems to be that the 2.4 by 1.5 meter fireproof panels, they were very, very good at withstanding heat and fires, but they offered pretty well zero resistance to an explosion because their design wasn't intended to handle an explosion. Hence, the first explosion tore them apart and allowed the fire to spread unchecked. This may seem strange, but the reason seems to be that the original design of the platform was for oil, which doesn't explode, but there was a retrofit of the platform in the late 1970s to allow for gas to be compressed and sent back to shore for processing. So originally, the excess gas was just flared. There's a big flare line, sticks out from the side of the oil platform, and they just torch it. It was waste. They didn't want it. But the government was pushing for stricter environmental controls of gas emissions and flaring, and they preferred the gas be captured, pressurized, and sent to shore for processing and use, rather than just burned as a waste byproduct. Oddly, in future, it turns out that gas was one of the preferred products because it burns cleaner with less CO2 emissions for the same amount of energy, even though it is slightly more expensive to process and to ship around. When the retrofit was done for that purpose, the newly added equipment passed through, or even components of it were contained within the original design modules, but there was no reassessment of the suitability of the module's firewalls to withstand that explosion. The debris from the first explosion's firewalls damaged a small condensate pipe that passed through Module B. That led to the subsequent gas leak, and that led to the next of the explosions. At that point, the smoking plume was the giveaway that fire was no longer fueled primarily by condensate gas, but had now ignited the crude oil. Crude oil, now on fire, also is a liquid and started to leak out of Module B, where it should have dropped down onto the ocean below through the diver's platform. The diver's platform consisted of a large series of steel grills, and that's where the divers would prepare for underwater maintenance of the rig. However, in previous years, the open grills, they were normally open woven steel grills, that would have let that oil drip away into the sea. Perhaps not good for the environment, but certainly it would have been a better outcome for Piper Alpha. But what the divers had done is they'd covered that grill with thick rubber matting so that the divers wouldn't be uncomfortable as they prepared for diving on the platform. Not sure if you've ever kneeled on steel grills, but it isn't comfortable. Unfortunately, this decision, made to improve their comfort, allowed the crude oil fire to pool and collect directly underneath a rather important pipe. The Titan platform was connected to Piper Alpha via pipework and fed natural gas pressurized to 120 atmospheres to Piper Alpha and from there off to shore. The pipework was now being heated by the crude oil fire pooling on the blocked up diver's platform. And when it ruptured, there was a fireball 150 meters in diameter. So big, it engulfed the entire platform. The Claymore pipeline connection failed last. Both Claymore and Tartan continued to pump oil and gas into the pipelines despite being able to see that something was seriously wrong on the horizon. They continued pumping of gas and oil by the Tartan and Claymore platforms was not shut down due to a perceived lack of authority, even though the personnel could see Piper was burning. There are so many lessons in design and safety that can be taken from this. So many. I can't cover them all. And again, it's been done. I just want to pick on two of them that mean the most to me. People will tell you that production pressures made the situation worse, and the valves should have been in the line of sight of the pumps, and evacuation routes should have been better planned. Other lessons people draw from it are the ability or confidence to stop the job, because the Claymore platform continued to pump oil until the second explosion, because the manager had no permission from Occidental Control Center to shut down, but there was a loss of communications, so they couldn't be sure, and they chose not to. Tartan also continued to pump, as its manager had been directed to do so by his supervisor. In both cases, it was cited that after a shutdown, it can take several days to restart production. That carries huge financial consequences. All of those lessons, they're true, mostly. But for me, the truly scary thing about how Piper Alpha happened in the first place is how it got started. And it comes down to two key problems: handover for multi-shift operations and permit to work. So let's talk about handover first. During the shift change, the note-keeping was extremely light. Very light on. The supervisor from the night shift was purportedly having another conversation, and the day shift engineer that was to provide an update on the status of the work during the day shift, specifically about the PSV they were working on, just placed the permit back in the box and left. And that's just unconscionable to me. It's absolutely vital that good summary notes are kept for handovers for communicating exactly what's happened on the previous shift. Not only that, it's vital for future investigations and fault finding and so on. Now, I've encountered a phenomenon where operators resist putting things in writing, especially things that were either running late or incomplete, where they played a part, not wishing to be held accountable. I'm not really suggesting that's what happened here, but it's a practice you should be aware of. In this case, I honestly think the day shift engineer was just tired and wanted to go on break, and the night shift supervisor didn't pay enough attention and didn't make time to talk with him first. Beyond that, it highlighted a lack of enforced written handover on the whole platform. It's a requirement that people write down all of the events that the next operator needs to know about, and they simply didn't do that. The big one is the permit to work. And the idea behind a permit to work system is that for a small subset of supervisors to be directly aware of exactly what work is being performed at any one time in a plant or a plant area under their control. It also provides a rigidity around risk assessment and job planning, and it serves as a record of the works that were performed. But the problem with Piper Alpha is that Occidental Petroleum that ran the platform had a permit system. They knew how important it was. So it wasn't the lack of the permits that was the problem. However, there was a flaw in their permit system in that the permits were grouped by physical location in the plant in different physical boxes. Now, because the pump permit to work was in a different box to the safety valve permit to work on the night of the incident, the on-shift operator only checked the pump permit. And because that pump had not had maintenance activities started on it, had no idea that there was a matching safety valve permit where the works had begun and had not been finished. The thing is, though, when you're planning a permit, you need to fill in any other affected devices and isolations. If I was preparing a permit for that valve, I'd say isolations, isolate condensate pump number 2. Isolations, during testing of safety valve, blind secured to flange. In the Piper Alpha system, it was acceptable to fill in a separate permit for the pump. I think that most engineers and technicians would have written why the pump was isolated, even if it was a separate permit. Either way, while the permit system had a hole in it, no system will save you if people don't follow it responsibly and think through the risks. Even before I started working in the oil and gas industry a few years ago, we studied Piper Alpha at university on safety courses, and countless inductions all cite, well, not all of them, but most of them cite Piper Alpha. What I've found fascinating is what different people take away from the incident. Recently, for example, I was speaking to a friend of mine that actually worked on an oil platform in the North Sea during the 80s, and he was there at the time during the Piper Alpha incident. Not on that platform, but on another one nearby. And he was told at the time that evacuation would be completely handled by helicopters via the helipad. You can imagine the reaction to the workers after Piper Alpha. I don't think they really trusted that anymore. So the problem with the helipad idea was that it was never going to work for a mass evacuation where you had a very limited amount of time. They said at the time that the engine on the helicopter had barely started and the rotors barely started turning by the time Piper Alpha was in the water. So lifeboats could have been launched from the deck level. If they had a better design, they could be launched from that level. There were more of them. They were more accessible. And the new lifeboats that they're using these days do a little duck dive under the water at a very precise angle, and they actually emerge away from the platform, safe distance away. But unfortunately, dropping from 80 meters above the water, when you hit the water, even at that angle, carefully engineered, you might hit kind of hard. And I suppose the sentiment is you might break a few bones, but rather broken bones than burned to death. It's interesting. It sort of reminds me a little bit of the Titanic's lifeboats. But whilst that is important, as an evacuation method. It's not actually what caused the incident in the first place. So let's circle back to that. Occidental Petroleum paid out millions in compensation to the victims' families, but no criminal charges were ever laid. Mass evacuation and rescues were never going to be effective via the helipad for any reasonable size fire. If you're dealing with something flammable, you have to assume someday it's going to catch on fire, and you have to have an evacuation plan that's going to account for that. But in order to prevent something like this from happening in the first place, if you're doing handover work, remember that your notes are critical. I know you're heading out the door. You want to go home, you want to take your break, and so on. But seriously, really seriously, take the time, go through the handover, and make thorough notes. Do it face-to-face with your back-to-back operator, your back-to-back engineer, technician, whatever, and make sure you make that time and make your handover to that person as good as you can. And just as importantly, make sure that they make the time. And if they're not, see that they do. Remembering also that the bad handover played a part in the BP Texas incident as well. But the big one for me about Piper Alpha, the biggest one, is take your permits seriously. They're not just some hoop that you got to jump through. I mean, they may well be something you got to do, but don't treat them like an annoyance. They're there for your protection, for the protection of everyone else that sets foot on that site, in that plant. Think through the details of what you're isolating. Make sure you're as thorough as you can be. I suspect that thorough, well-considered, thoughtful, well-rested, perhaps, engineers and technicians with a bit more time could have realized the potential issue of restarting that condensate pump. But in a high-pressure situation, in that scenario, when you've got production pressures and an imminent loss of power, along with all the perils of making these decisions on night shift, all it took was a flaw in the permit system, and it let this fall through the cracks. And 167 people died as a result of that. Isolate your stuff properly. Take your permits seriously. It matters. If you're enjoying Causality and you'd like to support the show, the best way is to become a patron via Patreon. It's at patreon.com/John Chidgey, all one word. If you'd like to contribute something or anything at all, it's very much appreciated. Causality is part of the Engineered Network. For other great shows, visit engineered.network today. This was Causality. I'm John Chidgey. Thanks for listening.